Hello and welcome back, students. In today's lecture, we will try to learn how to solve sorting problems using divide and conquer strategy. Previously, we learned how do we solve a binary search problem using divide and conquer strategy and a maximum minimum problem using divide and conquer strategy. There are two sorting problems that we will try to solve using this strategy. One is a quick sort problem and another is a merge search problem. Merge sort is an algorithm based on the idea of breaking down a list into several sublists until each sublist consists of a single element and merging these sublists in a manner that results into a sorted list. Today, we will try to learn how do we solve a merge sort problem using divide and conquer approach. But before I actually go into the merge sort problem, let's first understand what a sorting problem is. Assume we are giving a list of numbers. Let's assume we have 5 numbers. We have a 9, we have a 3, a 1, an 11, and a 15. In a sorting problem, our aim or objective is to sort these elements or order these elements in an increasing or a decreasing fashion. Say, let's assume if I try to order them or sort them in an increasing fashion, the result of that operation will be that 1 will take the first position, followed by a 3, followed by a 9, followed by an 11, and followed by 15. So this is a typical sorting problem. There are multiple ways of achieving this thing. There are multiple ways of solving this problem. One such way is what you normally call as merge sort. Now remember, this merge sort is basically following the idea of divide and conquer. I will try to reiterate here that in a divide and conquer strategy, we divide the problem into sub-problems, and those sub-problems then we try to solve them, and then we try to combine or merge the solution back so that we get the final solution. In this merge sort algorithm, the algorithm is primarily divided into two parts. We have a part wherein we try to divide the problem. So we have a part which let's call that merge sort. This is one function, and there's one more function that I'll be using. That function is a merge function. Now, the merge sort function over here, I will be using primarily to divide that problem into sub-problems. And using that merge, I'll try to solve that problem back and get the solution of the problem. Now remember, the algorithm basically works in two parts. One part wherein I will try to divide the problem, and the another part wherein I will try to combine the problem. Now first, let's see how do I divide this problem. Let's suppose this is my algorithm. Let's call this algorithm as merge sort. The merge sort algorithm will primarily keep track of 3 indices. One, the lower part of the array, the higher part of the array, and a mid value that I will be requiring. So I'll be using an index as low and another index as a high index. What do I need this? Let's have a look. Let's say the various elements in this array are 13. I have a 5, I have a 7, I have a 1, I have a 15, I have a 19, and I have a 2. This is my array, and how many elements do I have there? 1, 2, 3, 4, 5, 6, and 7 elements. Let's give proper indexing to these all these elements. So this at position 1, position 2, position 3, 4, 5, 6, and 7. So this low index and this high index that I'm using over here, the low will be pointing towards the first element in this case, and the high will be pointing towards the last element in this place. First, I need to know how many elements are there in the array that I need to sort. So to check that, what I do is that I check that with a condition that is my low still less than high. If the condition is true, that tells me that there are more than one elements present in this array and that I need actually to divide this problem further into sub-problems. So because of that, if this condition happens to be true, I need to know where do I divide this problem. To understand that, I need to compute a new value. Let's call that as a middle element. That middle element will be taken as the value of low and high, and I divide them by 2. Remember, in these cases, as we've seen in earlier problems, that we take the floor values. After I compute the mid value, I need to find out where exactly do I divide this problem. So what I do is that I recursively call the same function again. Remember, these divide and conquer strategies, they frequently make use of recursion. So I recursively make call of this function. So I call it the same function again, merge sort. Now this time the parameters that I am trying to pass over here is the starting initial first value, and where do I need to divide the problem, that will be the middle value. That's the first recursion call. There will be one more recursion call in this case. Remember, this is the left half of the array. I need to take care of the right half as well. So for the right half, what I do is that I make another recursion call. Since I have already traversed or taken care of elements from this element to the middle element, I need to take care of the rest of the elements. So I'll start from mid plus 1 and I'll end at high. Students, you need to understand in this case is that the first merge sort call is a recursive call to the same function. The first call will divide it into the left half, and the second call will take care of the right half. And we will keep on dividing until we get a singleton element. In the case of a singleton element, remember that a single element is always sorted. So we'll try to combine it back from them. After I've divided successfully this array, I'll try to merge it back. So what I'll be passing in this case is a low, a mid index, and a high index. And this is where we stop. Let's try to understand how does this algorithm work. Now if this is the problem, what is the value here for low? I'll just keep a track of indexes values here. My low is pointing to a 1. My high in this case is pointing to a 7. And if I compute a mid value, that in this case will be 1 plus 7 divided by 2, which is a 4. This is my mid value. So the call will essentially take these values, merge sort, my values will be 1 and a 7, high and low values. Now, before I try to solve in this case, let's do one thing, let's erase this and start solving this problem. If you can just remember those elements, these elements are 13, 5, 7, 1, 15, 19, and a 2. This is my low, and this is my high. So as of currently my low is a 1, my high is a 7. If I have to compute a middle value, that middle value will be 1 plus 7 divided by 2, where I get a 4. Now remember the algorithm, the merge sort function, it creates two merge sort functions. So earlier it's merge sort 1 and a 7. Once we go inside the function, we encounter two merge sort calls. Those merge sort calls are merge sort, let me put it MS in the shorter form, MS. So it will be from low and mid. Mid in this case happens to be 4. The next merge sort function, remember it's a recursion, so it will process every such recursive call by means of a stack. So my next merge sort function will be merge sort mid plus 1 to high. Mid plus 1 is 4 plus 1, that's 5, and my high is 7. And then after I have divided the problem successfully into 2, I'll try to merge it back. So this is a merge function, which contains a low value, a mid value, and a high. Now obviously what we can see over is in this case is that the actual array has been divided into two parts. What are the various elements in this case? 1 to 4. That's, I have a 1 here, it's a 13, it's a 5, it's a 7, and it's a 1. It's because of this merge sort call that it's been divided into two halves. Here you can vertically show the division. The second half, this is the left half and the right half. The second half in this case is my 15, my 19, and my 2. In the algorithm we can see that we always look for the condition if my low is less than high. Now the new low for this particular half is, new low will be 1, but the new high in this case is this 4, that's the mid value. So this is my new low for this half, and this is my high. And obviously low is 1 and high is 4, so the condition stands true, 1 is less than 4. So I'll try to call it again the merge sort function so that I can divide it further. a recursive call for this merge sort function will be merge sort. Low is 1, high is 4, my mid is 1 plus 4 divided by 2, which is a 2, because remember we are taking the floor in this case. So the merge sort function will be in this case my low and my mid, that's 2. There will be another merge sort function, because we are doing it recursively. There will be another merge sort function, that will be middle plus 1, that's 2 plus 1 is 3, and the high, that's 4. Then we have a merge function. Remember, that's 1, the middle element, and the high. Low, middle element, and the high value. We will keep on dividing this problem. Since this is not a single element, this is not a singleton element, so we will keep on dividing till we get those single elements. Now for this case, remember, if I see the elements, this array has been further divided into two parts. The first part consists of two elements, that's a 13 and a 5. And the second part in this case consists of two elements, that's my 7 and a 1. Again, the condition of low being less than high, because low points to 1 and high points to 2 in this case. Again, the condition low is less than high stands true. So we can make a further division, again one more recursive call to the merge sort function will be made, which will further divide this into a merge sort. Now in this case, my low is 1, my high is a 2, my mid in this case will be 1 plus 2 divided by 2, which is a 3, 3 divided by 2 is a 1. So the merge sort function in this case will be low is 1 and mid is 1. My second merge sort function in this case will be mid plus 1, that's 1 plus 1, that's 2, and a high is already 2, and I have a merge call which will take low value, mid value, and the high value. We can see that the low here in this case will follow it. The low in this case is pointing to a 3, and the high in this case is pointing towards a 4. So this is the third position, this is the fourth position. If I try to compute the mid value of these, then the mid value for these will become a 3 plus 4 by 2, which is 7. 7 by 2, if I take the floor value of that, that will be a 3. Now the next call parameters in this case will be merge sort. Low is 3 and the mid value is 3, that's merge sort of 3, 3. In the next call, it's merge sort of mid plus 1, that's 3 plus 1 is my 4, and my high is also 4. And then there's a merge call, which is for 3, 3, and 4. Let's first try to solve the first half of this, then we'll try and go for the second half of this. Now what we can observe here is that this merge sort of call, low and 1, let's see what element this is pointing towards this. The low and the 1 both point to element number 1. That element number 1 is 13. So we can see over here also it points to the element number 1, that's 13. So this is essentially the element 13 in this case. Now it's a single element. Remember, in this case the single elements are always sorted. You do not need to sort a single element because you are not comparing it with any other element. And the second element in this case, ms of 2 and 2, that's basically pointing towards this 5. These are two elements, and both of these are single elements. After, how does the recursion typically work? The recursion works, basically you divide the original problem into two subproblems. Now the other part of this problem, these recursive calls, they will be put on the stack, and we'll try to continue solving this problem. When I move from this left, I'm trying to complete the left cycle of this. When I try to move here, I reach the first problem. Now remember, this is a singleton set and it can be solved. Since it can be solved, once I reach this position, particular position, 13 remains solved. Why? Because there's a single element, it cannot be sorted any further. So my 13 is already sorted. Next, I take and go to the merge sort function of the second call, which points to an element 5. And remember always that again 5 being a single element is already solved. So we are already done with the second call as well. Now comes the third function call. The third function call, if you remember the algorithm, is the merge function. It's because of this merge function. Now merge function is pointing towards 13 and 5. The merge function typically operates on the fact that there are two sublists, or there are two these links. One is a left sublist and other is a right sublist. Now both these sublists are actually sorted in their independent. If you check them out, they are always sorted. When I take this merge function in next few minutes, we will try to understand how exactly this merge function works. Now remember, for merge function to work, both the lists, the left list and the right list, both needs to be sorted. In this case, that holds true. 13 in itself is a sorted list and 5 is a sorted list. What we will do is that we'll compare these two, 13 and 5, and try to find out, using this merge function, how do we sort these elements. Now if you see, we'll find out how exactly it works in a merge function. Now 5 here is a larger, smaller element than a 13, so we can put the sublist as a 5 and a 13. We'll come back to this using merge when we describe the merge function. This is the first part that stands solved. Let's go in the second part of this. Now here, this merge sort function divided these two elements into two different sublists. One sublist points towards the element 3, 3. If you see the 3, 3 element, that is the element 7. And if you see the other element that has been divided is element 4, 4. Element 4, 4 points towards the element 1. Now again, remember, these are two sublists which contain a single element, and single elements we already understand that they are always sorted. Now using this, basically we have completed this one half and also we have completed the second half. We can use the merge function call now to merge these two elements. When I try to merge these two elements, what I can see is that my 1 is smaller than my 7, so they can be put in like this form as a sorted list. What happened at the end of this is that I created two sublists, a left sublist and a right sublist, and these sublists are actually sorted, both of them. When I traverse back in recursion, now that I have completed the entire second call as well, I try to move towards this merge function. Using this merge function again, what we see is that we have two sublists. We have a left sublist and we have a right sublist. And this gives us the range where from exactly we are working at. So we are starting at the first element and we are going to the fourth element. So these are those four elements that we are trying to work at. Using the merge functions, we can actually sort them back. And if you check it out, what we see is that using this merge function, we will get the list as this: 1 and a 5 and a 7 and a 13. Just in case if you wonder how exactly did I get these values, when I go into the merge function, I will try to explain how exactly does this work. It's a very simple procedure. I'm just comparing the left list with the right list, and I'm trying to find out if there is an element which is smaller. Then what I do is that I make the necessary swap. I exchange the positions, and if the element that I'm trying to examine or compare with other element, if it's a higher element, then I do not make the swap. So that's we'll just check it out in the merge part. So this is my first half of the array that has been done. Likewise, in the similar ways, what we can do is that we can do the other half, the right half of the original array, that is this merge sort function. To make it look better, let me try to clean up some space for myself. Remember, this is the output of that first call that we have made here. Now in this case, my low is pointing towards a 5 in this case, this is a fifth position, and my high is pointing towards a 7. And if I try to compute a middle of these, that's 5 plus 7 divided by 2, what I get back is a sixth element. So when I make a merge sort call here, the merge sort call will be like this: the low, that is the 5, and the mid, that's the 6. The another merge sort function will be merge sort, mid plus 1, that's 6 plus 7, and high, that's already 7. And then the merge function. That will be a 5, a 6, and a 7. Remember, these are all pointers. These are all indices towards the different elements in the array. Now this particular merge sort call, we can see that the condition still holds that low is still less than the higher value. So we can make a further next call of this. In that case, it will be merge sort. Now the low is here 5. Let me try to do it here. The low is 5 and the high is 6. So if we see 5 plus 6, there are 2, there's a 5. Again, remember, I'm taking the floor value here. So it's a 5 and 5. Another call will be merge sort. Mid plus 1, that's 5 plus 1, that's a 6, and a high, that's a 6 again, and the corresponding merge function, which is a 5, 5, and a 6. Now, here if you check out, in this case, my low is no more less than high. So this is the condition where the original condition becomes false, and we cannot make further divisions. We cannot further divide the list into sublists. Now check out this element, 5 and 5. In the original index, if you find out that it's actually pointing to this value 15. So it's the value 15 actually that it is pointing towards. And the element 6 and 6, it's pointing towards the value 19. By the same logic that I used in the left half of this tree, we can check out that 15 in itself is a sorted element, so is 19. 19 is a single element which is always sorted. When I call I check this fifth element, it's a 15 element, it remains solved. I check for the next element, there's a 19 element, it remains solved. I go to the merge part of it. Now the merge part of it, when I try to merge these two, I can see that 15 is already, 15 is smaller than 19. So the merge will give me 15 and a 19 as a sublist. Once I complete this part, this merge part, this is how exactly recursion works for you. I try to go for the another call. Now this call will already be there in the stack. I'm trying to pull it out and try to solve it. Now merge sort of 7 and 7 is pointing towards this one element. That's my element number 2 here. Again, it's a single element and stands sorted. So this is my right half, this is my left half. Using this merge function actually, when I make use of this merge function, I'll try to merge these two lists now. When I try to merge them, this part and this part. When I try to merge them, I get another list that's 2, 15, and a 90. Now we are done with these recursive calls. We have completed our left half, we have completed our right half. And on the left side, what we have is that this is the sorted sublist, left sublist sorted, and this is the right sublist sorted. Using this merge function now back, what I will try to do in this case is that I will try to merge this sublist with this sublist in a sorted fashion. When I apply this, we will get the output of this entire algorithm will be a sorted list. Now remember, I'll just write it down over here. The left half points towards 1 and a 5, 7 and 13, and my right half is 2, 15 and a 19. I will use these values actually to demonstrate exactly how does this merge function work. Now using this merge sort function, what we achieved is that we have created two sublists, and remember both of these sublists, they are sorted. Now it's time to merge these sublists and try to get the solution, try to combine the solution. I have already written down the algorithm, and let's try to find out how exactly will this algorithm work on these sorted two sublists that we have created in this case. The algorithm here takes into consideration 3 different indices. There is a low that will actually point towards the lowest possible element, the first element. High, it will point towards the last element, and the mid that we will compute. I'm making use of some pointers here. We have a pointer that I'm primarily using in some loops. H is nothing but pointing towards the same thing which low is pointing towards. So is I, and J starts from mid plus 1. So if this is my array, which was earlier carrying 7 different elements, so this was a low and this was the high, and I used to compute mid from this low and high. Now remember, H here is pointing towards the same thing which low is pointing to, that's low. I is also pointing towards the same thing, while as my J is pointing towards mid plus 1. These are different pointers basically that I will be using in these loops. Now in this case, what I am doing is that I am running a loop. The loop I will run, remember H is starting pointing towards the first element. So in this case, it will keep on running as long as h is less or equal to mid, the mid value that is computed over here. As long as the condition is true, as long as h does not exceed mid, this condition will be true. But remember, I'm using an AND operator. That means both the conditions need to be true. Both the conditions need to satisfy. So I'm looking at the other half as well. So I'm taking from mid plus 1, that means the other half, next half. So from mid plus 1 till high, as long as I don't reach there, as long as this condition is true that my j is less than the high, both the conditions are true, this will keep on executing. Once either of these conditions is false, we'll come out of this loop and we'll come to this place. What are we trying to do inside this loop is that there are two ways basically of merging. One is that we can divide this into two different sub-arrays and try to run them on two sub-arrays. So first in this case will be like this. A of h will be pointing towards this element and A of j will be pointing towards this element. So I'm using the same array in both the cases. Or else what you can do is that you can use one single array, and then in that case this will be A of h here. Let's suppose, assume this is the mid, then A of j will be mid plus 1. So either way you can achieve the same thing using this algorithm. What I will be doing here is that I already have two sorted sublists. I will be trying to run this algorithm on these sublists and try to get the sorted array back. Okay, now h is pointing towards my first element here and my j is pointing towards mid plus 1. So what I am trying to do over here is that if A of h is less or equal to A of j, if A of h is less or equal to A of j, that's mid plus 1. If this condition is true, which it is, then I will create an auxiliary global array, a B array. This is my auxiliary array B that I will try to create over here. It's a global array. If this condition satisfies, if A of h is smaller than A of j, which the condition here in this case 1 is smaller than 2, the condition is true, what I will do is that I will simply copy this A of h and place it in my this auxiliary B array. So A of h will be in B of I. Remember, I have also initialized to low, so it will be pointing towards the first element in this case. So I will simply copy A of h is pointing towards 1, A of j is pointing towards 2. Is 1 less than 2? Yes, condition is true. If that is the case, then B of I, remember I is pointing towards low, sorry, B of I need to place A of h into B of I. What's there in the A of h is 1, so I'm just taking that element and placing it in the global array B. Okay, and since I have copied this one element, what I'm trying to do is that I'll increment my h. Now the h is pointing towards the next element. H is equal to h plus 1. Earlier it was pointing towards this place. Now h plus 1, h will be pointing towards this element now. Since the if condition is true, it will not obviously go into the else part. It will just increment the I. So my I will now point towards this element, the second element. And from here we'll go back into the loop. Is the condition still true? Is my h still less or equal to mid? Yes, the condition is true. Mid is my 4, h is my 2, so condition is true. Is my j still less or equal to high? We did not make any change to the j, so j is still pointing towards 5 and high is 7, so condition again is true. Since both these conditions are true, we try to again perform the comparison. This time around A of h in this case is now 5. A of 2, A of h is actually nothing but A of 2, and A of 2 actually is pointing towards the element 5. And A of j is pointing towards, that's A of 5, that's actually pointing towards my 2. Now we check the condition. Is my A of h less than A of j? Is my 5 less than 2? The condition this time around is false. Why? Simply because 5 is greater than 2, so the condition here is false. If the condition is false, we'll move from the if towards the else statement. In the else statement, what we try to do is that we try to copy that a of j, that element which is pointed towards by j. So a of j will try to copy that into the auxiliary array. That element in this case happens to be 2. So my b of I, now remember I in this case is 2, so that's b of 2. The element a of j, that's 2, we'll place that in this auxiliary array b. So we put this 2 here. And what we do after placing it there, we increment the j. Now the j is pointing towards the next element. Remember, when the if condition gets true, we increment h, we increment the left half, pointer in the left half. When the else condition gets true, we increment in the pointer in the right half. So my j is now pointing towards this element. Again, we'll go back and the while loop will check the two conditions. Is my h, which is pointing towards 2 in this case, is my h still less or equal to mid? Is it still less or equal to 4? Yes, that's true. And my j, which is pointing towards element number 6, is it still less than or equal to high? High has 7. Yes, the condition is true. Since both the conditions are true, we'll go inside the loop and we'll check again for the condition. Is my a of h still less or equal to a of j? Now remember, a of h in this case is a 5 and a of j in this case is a 15. If I compare 5 and 15 and check out whether 5 is less or equal to 15, yes, the condition is true, then we'll simply take this element a of h and we'll just take this element and place it in the auxiliary array b. Now I remember is pointing towards the third element. What I will do is that I will take this element 5 and place it in this auxiliary array b. I'll increment my h so that the h points towards the next element. Again, there will be no change in the j because I am not going into the else part of the algorithm, but I will make sure that I increment my I so that the I points out towards the next element in this case. If you see that this algorithm will keep on working like that till we reach a point where either of these two conditions gets false. Let's say that it works like that h keeps on getting incremented till it reaches this point and till it goes once it reaches this point, then the condition h is less or equal to mid is true, but if it gets one more increment, then h will start pointing towards mid plus 1, which makes the condition false. Now once that makes the condition false, this while loop will not run, will not execute, simply because this condition becomes false. It's very much understood in this case that the next element you will find out that will be copied here will be 7, and then we will have a 13 in this case. Once it reaches to 13, now we'll start taking elements from 15 and 19. Now remember, for this to execute, this is where the rest of part of the code comes in. If it so happens that either this condition or this condition, either of the two conditions gets false, if it's that my h goes beyond my mid plus 1 or my j basically reaches beyond high, then this algorithm, this part of the loop, this loop will not work. So in that case, what it technically tells us is that all those elements of 1/2 have actually been copied. Earlier, before we started, the two subhalves, they were sorted basically. So this is a sorted subhalf, this is a sorted subhalf. If either of these subhalves has been successfully copied into the auxiliary array, that means that all those remaining elements that are there are actually sorted. What we need to do in those circumstances is that we'll simply take those elements and copy them because they are already sorted, and the smaller elements out of these two subsets, they have already been copied. So all the remaining elements that are there can simply be copied into the auxiliary array. That's exactly what we are doing in this case. If my h goes beyond my mid, that means if my edge starts pointing somewhere after this, or else what we can say is that if edge goes beyond mid, I'm running a loop that's simply I'm using a new pointer k here that points towards the current value of j, and from here I will try to go to the last element. Whatever the elements they are there, a of k, I will try to copy them simply into the b of I in this element and keep on incrementing I till I reach the last point. But if h is not greater than high, greater than mid, that means h is still in this part, that means this part has already been copied, then I will try to copy remaining elements in this left half into this. So what I do is that I see wherever the current value of h is from this to mid. from h, current value of h to mid, whatever the remaining elements are there, I'll try to copy them a of k into b of I and keep on incrementing I. Once I'm done with this, what essentially I have done is that I have successfully copied all these elements from left half and from the right half of this into an auxiliary array B. Once we are done with this, I'm trying to run a loop again from low to high. So my k is this time pointing towards low, and I'm running loop from low to high. What I'm doing is that I'm copying all these elements from this auxiliary array back to the original array A. So B of k, that's B of k is here. B of 1 is copied simply into A of 1. B of 2 is copied into A of 2. B of 3 is copied into A of 3. B of 4 is copied into A of 4. Likewise 13, 15 and 19. And this is where we stop. And this is how we successfully complete the sorting problem using merge sort. One thing that you need to understand in this merge sort is that the complexity of this algorithm. Now remember, if you see that like a typical divide and conquer strategy, the way we use a divide and conquer strategy, here also the problem n is actually divided earlier into two parts. So what we can say is that it's divided into two halves. So that's 2 times t of n by 2 plus theta of n. Now see, there are two parts. One, if you remember the first lecture of divide and conquer, what we used to do there is that we used to divide that problem into halves. So we used to divide first into n by 2, then n by 4, then n by 8. So that if you see the tree, let me draw the tree for this problem again here. I was trying to look for the complexity of this algorithm. So let's say this is my array. I'll keep it very small. 15, 9, 3, 7, 1 and a 5. So what do we do using this algorithm? That we actually divide it into two halves. So I have a 15 and a 9 and a 3 here. And likewise I have a 7, 1 and a 5. And we will try to divide this further into a 15 and a 9, and the other half will be 3, and likewise here it will be a 7 and a 1, and the other half will be 5. This division, when we do say n by 2, this is my n by 4, likewise I'll go for next, there will be n by 8. Such kind of divisions what we learned last time, that they are basically these type of divisions, there we say that log n. When you come towards the end of this tree, here I get a 15, here I get a 9, this is a 3, I get a 7 here, I get a 1 here, and this is a 5. Now these are all possible elements. They were actually in their original array. I have a 15, a 9, a 3, a 7, a 1, a 5. Or in a more general, if you see in a more generic way, we can say that all these leaf nodes, basically, there are n number of these leaf nodes. So you actually need to work on those n number of elements. That's where we can say that we have to deal with all possible n elements. So we divide it, and we have the n number of elements that we need to work on. If you use the master theorem here in this on this recurrence relation, if you use the master theorem, it actually satisfies the second case of the master theorem, and you will find out that it actually is equal to order of n log n. So this is how exactly do we compute the time complexity of this merge sort algorithm. In the next lecture, we'll be discussing quick sort algorithm. Till then, have a good time.